Great, thanks, Peter. Thanks everybody for having me. The story of how I got here was I was at another conference a couple weeks ago, and I got an email from Steve Feinberg. I've been at CMU for a couple years now, primarily working with Steve. Steve sent me a note and asked if I could fill in for him at a workshop. So I looked up the workshop. I didn't know exactly what it was, and I was really excited because you guys are all doing really interesting work. And then I was really terrified because I had to fill Steve Feinberg's slot. So you're not going to get the kind of wide-ranging talk with very deep insights that you would have gotten from Steve. Most of you know Steve probably better than I do. So that's not going to happen. I've been working on record linkage for about a year and change now. And I think I've learned a few things that don't seem to be common knowledge. I'm going to try to share those with you today. But like I said, you're not going to get a Steve Feinberg talk. But I've been at a few of these workshops with Steve, and one of the things that he does that's terribly impressive, it's a long list of the things that he does that are terribly impressive, but I've actually seen him sit in these rooms and he listens to these talks, and I've watched him work on his slides, and he incorporates little bits of things that he hears throughout the day or the week, as the case may be, and then he tries to say something about how what he's doing and what he's thinking about relates to what everybody else is doing. So I've taken a pass at that in my talk today. Hopefully it goes off pretty well. If not, I still have my consent form, and I'll just tear it up and nobody will know that this ever happened. So today I'm going to be talking about probabilistic record linkage after indexing, blocking, and filtering. I'm going to define all of these words for you in a second. But first, just the motivation. It's the last talk of the last day, so I probably don't have to motivate this too much, right? So probabilistic record linkage is what we do when we take two files and we try to put them together without a unique identifier. Okay? So we've heard why it's important, right? We've got more and larger data sets all the time. They're available across a range of settings, industry, government, academia, wherever you like. And there's increasing pressure to do more with big data. And this big data is often found or administrative data, okay? The pressure comes from a couple of different sources, right? One is just that we have access to all this stuff now, so there's some sense that we should be able to learn from it. The other one is that the costs of traditional data collection are skyrocketing, right? Response rates to our surveys are dramatically declining, right? The sort of political polling we're doing now, where we call people up randomly on the telephone, in the US at least, they get response rates of something like 8%, and we've seen some pretty dramatic failures there. The sort of data collection that goes on at the US Census Bureau is really expensive, right? I mean, these are area probability samples, and then you're sending people to houses, and they're knocking on doors, and they're recording information, right? This stuff is all really costly. And there's some sense that with all this new data that we have and the administrative data that we sort of collect along the way, we ought to be able to kind of do more with less of that traditional data collection, okay? So that's why PRL is important. Now this data, this administrative data or found data, big data in general, it wasn't collected to be combined usually, right? Administrative data in particular was collected to administer government programs, okay? So it often doesn't have the sort of characteristics that we would like for data that we would collect, knowing that we're going to actually combine it later on down the road. Okay. So we've also heard why probabilistic record linkage is hard, okay? There are privacy and confidentiality concerns, okay? Regulatory concerns that are, at least in principle, driven by privacy and confidentiality concerns. Real data are messy, right? They may lack unique identifiers. We might not have thought to collect one, or there might be good reasons not to collect one. So an example that I like to use is the Survey of Income and Program Participation, which is conducted in the United States. The initial, I forget how long, panels of that survey, they used to ask for your social security number, okay? They stopped doing it because people would actually break off. They would say, I don't want to answer this survey if you're going to ask me for my social security number. They'd shut the door in the face of an interviewer. And so we lost a unique ID there, okay? For a good reason, right? We wanted to increase the response rates, get more representative data. We might have limited numbers of variables that are available for linking, okay? So the kind of stuff that you might want to collect if you're going to link two data sources is not necessarily what you need if you're trying to administer a government program or if you're Google and you're just running your website. So I'm not going to talk too much about privacy and confidentiality and regulatory concerns. I'm going to talk a little bit about messy data, but primarily I'm going to talk about computational costs, right? So if you think about having two databases or two data sets and you want to combine them, if you were going to do that sort of naively, right, you would have to compare every record in file A to every record in file B. So if the two files are of size n, that means I have to compare n squared records, okay? So that gets costly in a hurry. This computational burden has bred innovation. We've heard about a little bit of that today. This week. There have been a lot of developments in efficient indexing and blocking. Okay, Peter talked about some of them in his talk. I missed the tutorial, but presumably he mentioned them there too. He's got a nice book and dozens and dozens of papers. Becca's written a nice review paper a couple years ago with collaborators at CMU. So I'm not going to talk too much about sort of the technical aspects of how we do that. What I'm going to focus on is the fact that these procedures have important implications for inferring linkage structure. The way that we index, the way that we block, the way that we reduce that comparison space is important when we go on and try to actually infer true matching pairs and true non-matching pairs, and then ultimately make inference with a merged data set. Okay? That's primarily what I'm going to be talking about today. So I'm going to review some common index and blocking schemes. They're the sort of most common ways that people do this stuff is not the most complicated or the most efficient or the most advanced. And we'll talk about exactly what that is. So I'm going to discuss some of the implications of indexing and blocking using the Linkage-Center framework as a guide. So I'm also going to give you a little bit of an introduction to Linkage-Center. I think maybe not everybody in the room is familiar with what this actually is, but it's come up a few times in the talks today, so we'll spend a little bit of time talking about what it is. I'm going to propose some new modifications to Linkage-Center. You might think there wouldn't be anything left to do after almost 50 years, but it turns out that there is. And then if I have time, I'll close with some of the implications of the kinds of things I'm thinking about for other approaches to probabilistic record linkage and making subsequent inference with linked files. Okay. All right, so indexing, blocking, and filtering. What are these things? So like I said, the naive approaches to probabilistic record linkage would require just comparing all pairs of records in the two files. That's generally going to be impossible unless we have very, very tiny files. All right. So usually the first step after I've cleaned my data and made it look kind of nice is I'm going to index the files. Okay. So by indexing, I'm just referring to any method that reduces the number of candidate pairs that I'm going to consider for potential matching and potential matches. Okay. So I'm going to want to make coarse comparisons of these records, right? I'm going to want to do something that's very quick, because I'm going to have to do it n squared times. So these indexing methods should be computationally cheap. A special case of indexing is what's called blocking. Okay? Blocking is any indexing method that actually partitions records into separate blocks. What I mean by partitions records is that we end up with these blocks such that the only possible matches occur within blocks. So you get no matches across blocks. So simple blocking methods that you might think of would be to use something like a geographic unit, maybe the first 3 digits of a zip code in the US, a census tract or other geography, and just say I'm not going to look at records that actually don't, that correspond to people that reside in a particular geographic area. Right? Finally, there's filtering. I'm going to refer to this process of just dropping unlikely pairs after making a complete expensive comparison as filtering. Okay? So if I index, if I block, I get rid of a bunch of the candidate pairs. I have a bunch that remain. I might actually take an expensive hard look at them and then find out, okay, these are definitely not a match, right? They don't match on all these other fields. So what am I going to do with them? Maybe I'll just drop them. Okay? So maybe before I try to do any, estimate any probabilities, do anything else, I'll just say, all right, these are definitely not a match. Okay? I'm going to call that filtering. So obviously it doesn't help me computationally, right, because I can only do that after I actually compare those records, but it turns out that filtering is important in practice.
Jared, I just have a question, if you could go back just to your definitions. So if I understand it correctly, indexing, you're assuming that the partitions could overlap, is that correct? And then blocking, you're assuming they would never overlap. And then with the last one, the filtering, here are you assuming that the actual record pairs, for example, a partition is fixed, for example? I'm not sure what you mean by filtering.
So filtering just says, all right, so I do my indexing or I do my blocking, right? I do my comparisons. And then I get, say, a complete comparison vector, right? We'll define that in a second. But if I find out after I do that expensive comparison that the 2 records don't match on anything, I'm just going to drop them. So it turns out that filtering is not blocking, but it is indexing. It's just indexing that's not cheap. So getting back to the question that Becca just asked me, what's the difference between blocking and indexing? Blocking generates blocks, right? Partitions of records. So in this case, in file A, records 20 to 25 can only match records 0 to 10, let's say. Right? So the only matches can actually occur within those blocks. Okay? So what I really have are, in this case, 1, 2, 3, 4, 5 parallel record linkage problems because I can sort of partition each file and only look at the records that are in the corresponding block. Indexing is something a little bit more general. You can think about indexing as overlapping blocks. Okay? Like in this picture here. So there's no partition, right? I can't split the records into blocks. So like I said, blocking is really simple. We just sort of check if the record pairs agree on a particular key. Examples would include geographic units, like we said before. Maybe whether or not the records match on age, plus or minus some fuzz. Maybe we're going to look at whether or not they match on the first and last initial of the name. Those are all blocking keys that you might use in practice, but it's pretty clear that you probably don't want to just use one, right? So if I only look at records that match on the first 3 digits of a zip code or only match on a census block, I'm probably going to exclude some true matching pairs. So what you often see in practice is people will take multiple blocking keys, generate record pairs using each one, and then combine the results. Okay? So what's that actually doing? Well, for example, we might be doing something like we're going to retain all the record pairs that match on the first 3 digits of the zip code or the first and last initial. Right? I'm going to call this indexing by disjunctions of blocking keys. Right? The disjunction is just the or. You match on this or you match on that. If you match on either one, I'm going to keep you and take a harder look. Okay? So my claim is that, at least in the applications I've seen, indexing by disjunctions is the most common way that people index. Okay? It's easy, it's cheap, and they're really efficient software packages that will do it for you. Okay? So indexing by disjunctions, it's a robust version of blocking, right? Because I have an or. So if you just look at this simple example, I've got 3 records in file A and I've got 2 records in file B. If I was going to block them on something like, say, the first initial of their last name, right? Well, it's pretty clear that I'm going to lose this first record pair. I'm going to lose my Janes, right? Because I have Jane Calder with a C in file A and Jane Calder with a K in file B. So if I were to block on the first initial of the last name, I'm going to miss those guys, right? I'm going to have a false non-match. So that's undesirable. All right, maybe I should match on the first 3 digits of the zip code. Well, if we look over here, if we look at our Heathers, right, Heather Porter over here and Heather Porter over here, her zip code is recorded wrong in one of these places. I don't know which one's right. So if we were to block on the first digit or the first 3 digits of the zip code, I would exclude that pair, right? So that's a bummer. But if I were to block on the, or sorry, if I were to index by the disjunction of those 2 blocking keys, I would retain all those pairs, right? I would keep my Jane-Jane pair, I would keep my Heather-Heather pair, but I would exclude all the Paul-Jane, the Paul-Heather pair, right? Those guys would be gone. So I get some reduction of my comparison space without increasing, in this case, my false non-match rate at all, right? So just a little bit of intuition for why we might actually do this. So indexing by disjunctions, this is not generally blocking, right? I don't generally get blocks when I do this. So I have blocking over here and I have blocking over here. I take the union of those things. You can think about that as just I have a 1 in my new matrix anytime I had a 1 in the original matrix on the left or in the original matrix on the right. So in general, I don't get back blocks because I took the unions. Right? OK, so I told you that, and hopefully you believe me. Then the question is, does the distinction matter? And I'm going to claim that it does. And I'm going to claim that it does in particular for Pileggi-Sunter type models, for any model-based record linkage procedure, really. And also for Bayesian methods, okay? So blocking is desirable for a couple of reasons, right? The first one is that it has computational benefits, right? It sort of pulls this problem apart into some number of parallel record linkage problems that I could sort of consider independently and maybe solve in parallel if I don't need to actually sort of use information across the blocks. On the other hand, if I do want to use information across the blocks, it's a really convenient structure to do some probability modeling, okay? And that's been done in a Bayesian context by Tancredi and Liceo. Mike Larson in a tech report, and lots of other people, actually. Okay. The other thing that indexing by disjunctions does is it implies new and different constraints on the models that we should be fitting. And I'm going to be more specific about that in a minute. Okay. So what's the relationship to between indexing by disjunctions and some of the more recent indexing methods we've heard about. Well, a lot of these things generate overlapping blocks, just like indexing by disjunctions. Okay? So Peter talked the other day a little bit about sorted neighborhoods, right? So I sort my two files, and then I just kind of pass a sliding window down them. That generates, if you think about that matrix that showed sort of admissible comparisons, that generates something that's like band diagonal, right? So not blocks. Q-grams, canopies, various hashing variants, all these things generate overlapping blocks, the same way that indexing by disjunctions does. Okay? I'm not going to actually talk about them in depth. I don't really have time, but the point is that this sort of structure is really common. But again, indexing by disjunctions of simple blocking keys, the really simple methods I just described, that's probably the most common way that people actually do indexing in practice. Okay? So here's an example that we care about a lot. John was asking yesterday if we could apply a particular method to a file that had 300 million records. This is why. Deduplicating the United States decennial census. There's a nice paper by Winkler and his collaborators where they went back and they used data from the 2000 census that was collected during the post-enumeration survey to try to actually learn a blocking scheme. Okay? So the post-enumeration survey in 2000 gives us a set of known links and non-links. Right? There's really extensive clerical review and things to actually determine who matches in the post-enumeration survey to who matches in the census. So this is what they came up with. They decided to index by disjunctions of these various blocking keys. So the first blocking key is the phone number. The second blocking key is matching on the state, the county, the block. Okay, so a geographical unit, the first initial of the first name, the first initial of the last name, and then all the way down. So they considered something like 11 different keys. They actually sort of looked at what the false non-match rate would be for different blocking keys, and they arrived at this based on some combination of false non-match rates and computational efficiency. Okay. All right, so that's indexing and blocking and indexing by disjunctions, which is a particular form of indexing. What about filtering? So if we come up with some indexing scheme, and it turns out that pairs that are just empirically really unlikely to match survive our indexing scheme. Okay, so even though we did our indexing, they're still in sort of our admissible set. What should we do? Should we get rid of them? Even after we've made this comparison, right? So the computational cost is spent, most of it anyway. We've actually made the comparison. Should we throw away those record pairs? Okay. Here's a plot. I'm not going to try to explain it too much, but it turns out that Steve Feinberg and his PhD student, now a postdoc with Jerry, Mauricio Sadinley, they had this question. They were doing a multiple file variant of the kinds of things I'm going to describe today. It's not super important that you unpack what it is. But they had a related question, which was, should we do blocking if we don't have to? So if we can actually compare all the record, in their case, triples, should we just go ahead and do that, or should we block anyway, even if we have the computational resources to do it? So they just looked at it empirically. So in this plot, just focus on the top left. We're looking at misclassification rate, basically. The solid black line at the top, that's around 20%. That's the error rate without blocking. The dotted line that's down near 0 is the misclassification rate you get if you block. Okay? So 20% versus something like, I think, 3 or 4% error rate. All right, so it's clear that there's something going on. It's clear that I get better inferences if I block, even if I didn't need to computationally. Just empirically, we see that. So the conclusion in the paper was basically evidently, yes, it would be helpful to block even if we don't need to, but we're not really sure why. And today I'm going to try to give some reasons why that might actually be the case. Okay. So just a couple other comments about filtering. It's a very special case of indexing by disjunctions. That's pretty clear if you think about it for a second. It's very common in practice. So the software that I told you about that was used to actually do the deduplication in the 2010 census, it filters. Okay, so it drops pairs that are extremely unlikely to match, that survive all the blocking keys. Okay. So there are at least 2 reasons to do it. The first one, of course, is computational, right? So usually the most expensive computational part of probabilistic record linkage, at least in Filigi-Sunter, is actually making the record comparisons. So one reason, but it's not free subsequently, right? So I still have to do more stuff with that record pair after I've made the comparisons. I think the primary benefit is robustness to particular modeling assumptions that I'm going to make precise in a second. The problem is that filtering does some very particular things to the space of all possible record pairs that needs to be accounted for when you make subsequent inference. and it rarely, if ever, has been accounted for in subsequent inference of linkage structure. And I'm going to talk about how we can actually do that. Okay. So before I do that, I'm going to actually tell you about the Filegi-Sunter framework. Filegi-Sunter provided what I think is probably the first methodologically rigorous development of probabilistic record linkage. Not the first, but the first to be really precise. I think John made this comment the other day that if you look back in the stats literature for who wrote the original things about a particular method, Ivan Filegi's name is usually on it.
Official statistics.
That's right. And these methods are still extremely common in practice. They're used everywhere. Becca made this comment in her talk yesterday as well. So the basic idea is this. Suppose I have two files A and B with records little a that reside in file big A, little b residing in file big B. We're going to make Q binary comparisons between record pairs. Okay, so do they match on a particular field? Do they match on some other derived comparison? It doesn't really matter. Okay, so I'm going to collect these in these vectors gamma A, B. In general, they don't have to be binary comparisons, but the exposition's a little bit easier if they are, so let's just go ahead and assume it. And my goal is to partition these record pairs A and B into the set of matches and non-matches, which I'm going to refer to as M and U. And I'm going to do that using these comparison vectors. Okay, so for the purposes of doing record linkage, the comparison vectors are my data. All right. The Filegi-Sunter framework is based around a very simple model for these for the data, for the comparison vectors. It's a two-component mixture model where the components correspond to true matches and true non-matches. Okay. So the probability that a record pair A and B is a match is just going to be denoted by PM. Okay. The probability of observing a particular comparison vector G, given that the record pairs are truly a match, is just going to be pi sub G given M. Pi sub G given U is just going to be the probability of observing a particular comparison vector, given that the records A and B are truly not a match. Okay. So of course, we don't actually have true match and non-match status. What we actually see is observations from this marginal distribution here, which is a mixture between the truly matching and truly non-matching components. All right. The nice thing about the reduction to comparison vectors is that it lets us sort of reason about what pi g given m and pi g given u should be. Okay. So if you think about pi g given m, well, if there were no errors in recording things, that would just be 1, right? You would just match all the time. If we didn't have recording errors, transcription errors, measurement errors, all the sorts of things that happen to our data, right? That would just be 1 all the time, and it's not, right? Because we actually do have all these things in practice. Pi g given u is a combination of things. So in principle, it's possible that you have some sort of measurement error that kind of induces random agreement between two records that actually don't correspond to the same person. And it also has just random match stuff embedded inside of it, right? So if you only compare records on something like their birthday, we have an idea of what the probability of random agreement on birthdays is, right? This is not intro probability, so I won't actually go through it, right? But we could all compute that if we wanted to. So what I'm going to do today in this talk is I'm going to take this seriously as a model for the contingency table of comparison vectors. And think about what happens as I do the indexing, the blocking, and the filtering. Think about what happens to my parameters. There are some reasons why we might not want to do that. Okay, Becca mentioned a few of them in her talk. These record pairs, they're not independent, obviously, right? Because I got them from comparing files from records in one file to records in another. And there's a particular sort of really simplistic model for the linkage structure that's kind of living behind here, basically that the probability that two records match is independent from the probability that any other two records match. Okay. But it gives us a sort of useful framework for thinking about some of the issues that come up when we start indexing, blocking, and filtering. Okay. So the first problem I'm going to have is that I have a contingency table here, right? A 2 to the q table. In general, I can't fit these saturated models, right? So I have so if I have 7 comparisons, I have 128 probabilities here. Maybe that's okay, but if I have many more than that, I'm going to get in trouble in a hurry. So people often fit reduced models. A particularly common one is conditional independence model, where we just assume that the probability of agreement on any field is independent from the probability of agreement on another field, given that I know your true match status. Okay? So this is just a latent class model, if you're familiar with those. Naive Bayes, if you come from sort of a ML, CS type background, that's the model we're dealing with. It's not necessary to do so. You could fit other sorts of non-saturated models. Yves Thibodeau did this, various interactions in log linear models. You can impose constraints on some of the margins, things like that. But I'm not really going to talk about that because it's not essential. But this model actually gets used a lot in practice, this conditional independence model. It's usually the place where people start. Okay. So all right, so that's the model for these record comparisons. The reason I'm modeling record comparisons is I want to actually decide which records are truly matches and which records are truly non-matches. Philae Center provided a decision rule for actually doing that. Okay? The idea is basically as follows. We partition our comparison space into 3 pieces, gamma m, gamma u, and gamma c. All right. Gamma m is just going to be the match region. So if I observe a comparison vector in gamma m, I'm going to say those records match. Gamma u is the non-match region. So if I observe a comparison vector that lives inside of gamma u, I'm going to call that a non-match. Gamma c is the indeterminate or the clerical review region. If I observe a comparison vector in there, I'm going to send it for further review because I'm not sure. Okay? It gives me a I don't know option in my decision rule. All right? The partition into this space is determined by these matching weights. Okay? It's just a likelihood ratio, right? So it's the likelihood of a comparison vector being a match against the likelihood of a comparison vector being a non-match, which I can estimate using the model I just described. I can compute these weights and do effectively just a likelihood ratio test. So it's a pretty intuitive thing to do, right? So if the probability of observing a vector given that it's a match is much larger than the probability of observing a particular vector given that the records are truly a non-match, if that's large, right, we want to put it in gamma m. If it's small, we want to put it in gamma u. Okay? So that's how we're actually going to infer the partition. The idea is just this. So we look at the space of log weights, and we determine two thresholds. Here?
Excuse me.
Yeah.
I just missed it. Can you explain how you estimated these probabilities?
So I compute these comparison vectors, and then I just fit this model with maximum likelihood.
But you don't know which are true matches and which are not.
That's right.
So
So I get, sorry?
Use EM algorithm to estimate that.
So I don't actually, to compute these weights, I don't actually need to know which particular record is a match and which particular record is a non-match, right? So it's not quite a likelihood ratio test, right? But I can estimate these parameters, and I can get estimates of these weights.
Can you elaborate a little bit on maximum likelihood? Because this isn't a true it's not a true likelihood, because
Right.
you pointed out you don't have independence.
That's right.
So what is it?
It's maximum likelihood under a misspecified model.
Well, it's some. Well, what is that? I mean, you talk about kind of using properties of maximum likelihood estimates, but they're not correct. So
I'm not going to actually use any of the properties of maximum likelihood estimates, right? I have an objective function. I'm going to maximize it, okay?
Okay.
It corresponds to maximum likelihood under a misspecified model, right? Maybe I should have given a stronger caveat here.
But sorry, I mean, when people talk about maximum likelihood estimates, we talk about that because they have certain desirable properties. But you just demonstrated that these aren't maximum likelihood estimates, you pointed out. That's not disputable. So why is this algorithm, in some sense, the one you want to use? Is it optimal? Are there other algorithms? That, relating it to maximum likelihood, it doesn't hold any ice because you haven't got maximum likelihood. You're not doing maximum likelihood. So what's it? I agree the EM algorithm gives you an answer, okay,
Yep.
and it's minimizing some objective function.
That's right.
It'd be nice to have an explicit kind of version of what that objective function was. I don't know whether you can write that down.
I mean, it's that, right? I mean, it's that with the appropriate products and things, right?
All right, but why is that a good objective function to minimize?
It's a fair question, right, given that this model is misspecified.
Yeah.
It's a perfectly fair question.
Sorry, this has always puzzled me because that's what the literature
Yeah.
seems to assume. And when you read people, they kind of talk about maximum likelihood as if this is incontestable, but of course it's not. And so I just wonder whether any other grounds on which you would want to justify this as the right objective function to use.
So I'm not going to try to justify. So the way I kind of backed into this was I wanted to understand what people were doing. And this is what people are doing. So I think it's useful to think about the parameters I get out of here as maximum likelihood estimates. Even though the model's wrong, the model's clearly wrong. We could go down a whole list of reasons why it's wrong. But what I want to do in this talk is I want to think about how those estimates change. I want to think about how those estimates change as I remove data. And thinking about sort of the implicit model that's behind here, even if it's wrong, is going to give me some idea of how I can think about how those estimates are going to change as I remove data.
Can I just say one more thing?
Yeah.
Sorry, I think this is an important question, because if you use a different objective function,
Yeah.
and the kind of in a sense there's an infinity of possible objective
Sure.
functions you could use, you will actually get different sets of weights that are actually also in different rank orders.
Yeah.
And therefore, your threshold decisions are not going to be monotonically related
That's right.
to each other under different
Yep.
optimization procedures.
Yep.
I see it's me an important issue.
It is.
You're going to.
It is. We're going to talk about that. I'm going to actually talk about sort of a refinement of that. Maybe it's a reasonable place to sort of stop and talk about the history, right? So Filegi and Sunter, the paper was written in 1969. EM existed, but we didn't call it EM, and it was in sort of weird pockets of the literature that they didn't know about. So the initial ways that people estimated these parameters were by the method of moments, okay, or using historical data or things like that. And you're absolutely right. You get completely different estimates. Doing maximum likelihood even under this misspecified model is kind of nice in that regard because the estimates are more stable than the method of moments estimates. So that's one reason why you might do this instead of that.
In the paper, they actually solved. They had 3 variables with, so that turns out to be 7 parameters, and 7 equations or 7 equations. Anyways, they solved it in the paper in pen, actually.
Yeah.
I think that's a well-known result. And actually, when you try and do this stuff in practice, you find you often reach local minima,
Yep.
and things are kind of sensitive to starting points. A lot of software doesn't allow you to change the starting points. Also, there's some real practical problems, I think, with using these algorithms.
I would agree with that. I'm going to try to solve a few of them, and some of them are basically insoluble. So sort of the broader roadmap is this is not where I want to stop. I want to think about the effects of indexing, blocking, filtering on probabilistic record linkage. I'm starting with Filegi Center. That's the stuff that I have worked out, so it's the stuff I'm going to talk about today. Ultimately, I want to extend that to more modern ways of approaching record linkage. Okay, but this is maybe crawling before I walk is a way to sort of characterize the stuff I'm talking about today. Yeah.
Just as a query, there are models for correlated data contingency tables. So you could extend this, could you, by introducing some sort of correlation structure in there?
Yeah,
And then
sure.
see where your EM algorithm takes you?
EM gets difficult, right? The E step gets hard if you do anything other than just assuming these things are kind of exchangeable.
Throw
Yeah.
a parameter in to keep you throw in the Harvey's parameter. You throw in a couple of parameters just to sort of keep people happy and then keep going.
So the E step gets hard. So imputing so if you have dependence between whether A matches to B and whether C matches to B, say, which would be a reasonable thing to do, the E step gets really complicated in most of the.
But numerically, the E step, can you get numerical?
You can use simulations. I mean, it's challenging, right?
Yeah.
I haven't tried it, but I've sort of written it down and looked at it, and it looks hard.
Okay.
Okay. All right. So if we assume I can fit those models and I can get these parameters, or if they're just sort of handed to me, I can use the results in Filegi Center to determine the partition of my space. In my case, it's 2 to the q, right? It's a contingency table. The cells near the 1, 1, 1, 1, 1 cell should be in gamma m. The cells near the 0, 0, 0, 0 cell should be in gamma u. And there's going to be some place in between where I'm not sure. Okay. And they give a way of deriving this region based on the matching weights. I won't actually talk about the picture. It seems like you guys are maybe a little bit more familiar with this than I thought you were, at least some of you. But the idea in Pileggi-Sunter, the original motivation, I think, as Becca mentioned yesterday, it's really an extension of just like classical Neiman-Pearson hypothesis testing. So we're going to fix a type 1 error rate. We're going to fix a type 2 error rate. We're going to solve for we're going to solve this equation, right? So the type 1 type 1 error under our model, right? That's just the probability that I observe gamma AB and gamma M, whatever gamma M happens to be, given that the records were truly a non-match, right? Under my model, I know what that is, right? So I just sum up the pi g given u over gamma m. That gives me the probability that I see a comparison vector in gamma m, given that the records were a non-match. Okay, I can solve that for any mu, and I can do the same thing for lambda. The way I actually do that, right, is I start with, so in my case where I have binary comparisons, I start with a 1, 1, 1, 1, 1 cell. I look at pi of 1 given u. I compute the probability. If it's not quite mu yet, then I find the cell with the next highest weight, and I put that in gamma m, and then I recompute. And then I find the cell with the next highest weight, and I put that in gamma m, and I recompute. Okay, that's the basic idea. So really, I just need to sort the comparison vectors by their weights, compute a cumulative sum, and then solve for which cells go where. Okay, so it's really straightforward. And then sort of whatever's left over is gamma c, right? And the result in the paper is that this procedure will, among all the decision rules that have error levels mu and lambda, it's going to minimize the size of that clerical review region, right, that indeterminate region. So that seems like a reasonable thing to do. On its face, there are problems. The error rate estimates are notoriously unreliable. This has been written about extensively. There are a lot of moving pieces for why that's the case. Harvey pointed out that the model is fundamentally misspecified, right? So the estimates I get back maybe don't correspond to the truth. That actually gets even worse when we start thinking about fitting some of these reduced models, right, like conditional independence models and things like that. We're just sort of increasing the degree of misspecification as we go. I will also point out that from talking to people who implement these procedures, these error rates are very often misunderstood because they're type 1 error rates, right? A lot of us have taught intro statistics. People would rather think about mu not as the probability of observing gamma in the acceptance region, say, given that it's a non-match. They want to think about the other probability, right? They want to think about the probability that a record pair is a non-match, given that I called it a match, right? They want the probability of H naught given the data, not the probability of the data given H naught. This is remarkably common among people who are actually using these things in practice. It really shouldn't surprise us, but it's like leaked into the literature and things and doesn't sort of get eliminated in peer review, so I thought it was worth pointing out. It's also, oops.
Are the error rates bad also if you use something like cross-validation or something? So is it because
if you have labels true matches and non-matches, you can do much better than this. Right? Yeah. Peter's written a book. Right? Of what you can do if you have labeled matches and non-matches. You can do much better than Pileggi-Sunter. Yeah. So that would be one way to sort of correct the estimates from like a naive thing with no labeled pairs. Would be to do something like that. Ooh. Okay. All right, so that's the basic framework for Pileggi-Sunter. Now I want to start thinking about what happens as I implement blocking and indexing and all these things. Okay. What does that do to the estimates that I get out of these algorithms? Okay. So effective indexing, blocking, whatever you're doing, it's what I would call a missing data solution. I'm used to dealing with missing data problems. That's what most of my early research was on. Indexing is a missing data solution. We're going to solve our computational problems by indexing or blocking or whatever. So if I'm doing a good job, the missing pairs, the pairs that I take out of that table, they're going to be disproportionately non-matches. That's what I'm trying to do, right? So if you're familiar with missing data problems at all, what you've done is you've generated a non-ignorable missing data problem. Okay? And you shouldn't expect the parameters that you estimate after you do that to correspond to the parameters you would have estimated had you not done that. So this isn't necessarily news. There's some discussion in the literature about this issue, but nothing really systematic, and people aren't really sure how to think about it. So I wrote a paper, this JPC paper, and most of the stuff we're going to look at today is in there, if you're curious. So I'm going to walk you through some of the main ideas. So the idea is really simple. So if we take our simple two-component mixture model seriously, what we get after we do blocking is something like this. So we can define a new comparison beta AB, and that's just going to be 1 if the record pairs A and B agree on some blocking criteria and 0 otherwise. Okay, so just an additional comparison. Okay, and so now everything that I'm doing is conditional on beta. Okay, so I've just conditioned everything on beta all the way through. Simple enough. So you might wonder what correspondence, if any, is there between the parameters in this model versus the parameters in the model a couple slides ago. Okay, we know they're different because we did this not ignorable missing data process ourselves. We designed it. We did it on purpose for good reasons. So how do the parameters in this model correspond to the parameters in the model I just showed you? Well, you can just sort of reason about it, right? So the proportion of matches after I blocked should be much bigger than the proportions of matches before I blocked. Otherwise, something went horribly wrong, right? These comparison vectors here, sorry, the probability of comparison vectors given that the pairs are a true match here, right? So pi g given m, that shouldn't change very much, okay? So think about taking all of the record comparison pairs out of the second component, out of the non-match component, then pi g given m and beta would be roughly the same as pi g given m. Okay. Pi g given u and beta, on the other hand, is going to be different. So when g is very close to the 0 cell, this probability is going to be very small. Okay. If we've disproportionately removed non-matching pairs from our data, so think about an extreme case where I have some really effective blocking and I can actually get rid of all the observations in the 0, 0, 0 cell. Now pi g given u and beta is going to be 0, right? If I had a really good blocking scheme.
So given beta means being in the same block?
Sorry? Yeah. Everywhere you see a beta means that the record pairs agreed on a block. Yeah. And then, of course, if those probabilities go down, some other probabilities have to go up. And it's going to be the ones that are actually really close to the 1, 1, 1, 1, 1 cell, right? Those are not going to be removed by most of our blocking schemes because they're not magic, right? So these conditional parameters are actually the ones that I care about, right? I don't want to use estimates from this model to say anything about the record pairs I excluded from blocking, I claim, because you need some really strong modeling assumptions, and Harvey's already unhappy with the ones that I've made, so I'd rather not make any more. Right? So I'm going to argue that we should actually focus on these conditional parameters and use these to estimate our error rates and see how well we can do. This is sort of effectively what people are doing in practice, but they're not really thinking about it. And it's going to matter in cases like the one I just described where we actually poke a 0 in this table. Okay. I'm going to skip this, but I think that the way that we set the thresholds, even if you will sort of grant that I can compute these error rates reasonably well with my model, is probably not a good idea. I'm rapidly running out of time, so I won't talk about that. So now let's imagine that I do an initial blocking pass, say just traditional blocking. I keep things that match on census block, something like that. And then I do more indexing, right? So I start dropping pairs that don't agree on the first and last initial and things like that. Well, this subsequent indexing step can actually poke structural zeros in the contingency table, okay? And something like filtering always does, right? So I might say, after I've made my comparison, I'm just going to throw out all the data in the 0, 0, 0 cell, because why not? I'm never going to come up with a decision rule that says call everything a match, so I might as well just throw that data away. So if we just think about a toy example where we have two comparisons, q is equal to 2, and we're going to do blocking followed by just filtering on their disjunction, right? So we're going to say throw away everything in the 0, 0, 0 cell here. Right? So what are we actually doing? Well, this is our original data. So if we did all the comparisons, we would have this three-way table where I've got the beta 1 face and the beta 0 face here, and then just the cross-classification into gamma 1 and gamma 2, okay? And just their counts. I have a model for this table. So what happens when I block? Well, I say I just don't care about the beta equals 0 face. I'm not going to worry about it. I'm not going to compute those pairs. I'm not going to think about them. I'm just going to sort of proceed and do what I wanted to do in the first place. Okay? That's blocking. Filtering, or indexing by particular disjunctions, ignores that cell, right? Ignores that 0, 0, or sorry, N0, 0, 1, right? So pairs that match on the blocking criteria but don't match on anything else. Right? So I'm going to poke a 0 in there. So what does that do? Well, it induces another layer of misspecification if I don't have a model that actually accounts for having done that, right? So if I just go ahead and fit a model that assumes my structural zeros were sampling zeros, I'm going to have a problem. And just sort of thinking about it heuristically, I'm going to have a really big problem because there was a lot of data in that cell, right? For most of the common blocking and indexing type schemes that we have, even after I block once, I have a lot of data that doesn't match on anything else. Okay? So I have a fairly serious problem. We can write down a model. I'm not going to step through that. The implications are basically the same. The parameters change in a similar way. The new thing is just here, where I've actually restricted the support of the comparison vectors by doing this filtering step. Now again, this filtering step is really, really common. It's inside the big match program that's used at the Census Bureau. That's sort of the backbone for all these big matching projects. So this is happening. This is in the wild. So what am I going to do? Well, like I said, treating structural zeros as sampling zeros, it biases estimates. Jerry and Postdoc have done some work on this in a different context. So what are we going to do instead? Well, I propose a simple sort of reduced form model for dealing with this. It's the extension of conditional independence models to the case of quasi-independence. Okay? It's not super important to unpack what this is. Quasi-independence are just log linear models with no interaction terms that I subject to the support restriction. So you can think about taking that conditional independence model I described at first and just truncating each of the components so that it puts 0 probability in that cell. Okay? So now those comparisons can't be independent, right? Because we have to make sure that we put 0 probability in that cell, but it's as close as you can get in some sense, right? You still have this multiplicative model and a far fewer number of parameters. Okay. So some data examples. I'm going to kind of whip through this one because it's in the paper. So it turns out that actually if I try to estimate these error rates in a context where I know the truth, I get much better estimates of the error rates if I block and then filter and then fit this conditional quasi-independence model. Okay? Just really quick, this is the relative error in the estimate of the error rate as I sort of add cells. I haven't told you what these cells are, but this is matching on first name, last name, year, month, and date of birth. And then as I sort of add cells according to their estimated weights, in this case I get the same rank order of weights if I filter versus if I don't filter, no matter which model I fit. But I get much better estimates of these error rates using the conditional quasi-independence model than using the conditional independence model. Okay?
What's the size of the data?
This is RL data 10,000. Yeah. So sure, we can go through some numbers, right? So this is deduplication. So I'm matching a single file to itself. The original file has 10,000 records. So I have about 50 million pairs. I block on the first initial of the first and family names, right? So you have to match on that. That gets me from 50 million pairs to 370,000. Then I do this additional filtering step, and I just say, all right, anything that doesn't match on at least 2 comparisons, I'm going to throw it away, right? That's my filtering step. The filtering step takes me down from 370,000 to 35,000. Okay? So 90% of my data was in that sort of corner down there by the 0 cell. And I threw that away, and I fit the conditional quasi-independence model. My claim, and I don't have a proof, but my claim is that the estimates I get from that model are going to be sort of less biased than the estimates I get from the original model, because even though they're misspecified, I'm only feeding it the data for the parameters that I care about. Okay? So empirically, that seems to be the case. This is the picture that says so. I looked at doing it in various different ways. We still get better estimates of these error rates. That seems to be persistent. So let's look at an actual real data example, one that's a little bit bigger. So in this case, I have 100,000 records from a cancer registry. In this case, I only have the comparisons. They were just sort of handed to me. So I have 7 fields in this case: first and family name, year, month, date of birth, sex, and postal code. So this data was actually indexed by disjunctions before it ever arrived to me. In the documentation, this is what they did. It's not super important that you unpack that. But each record pair had to match on one of these blocking criteria, or it didn't make it into the data file. So if you had a minute to read that, it would occur to you that actually this process induced structural zeros in the table. They're there. In particular, if I don't match on any of the name fields or the date of birth fields, that record is just gone. It doesn't make it into the final data. So there are zeros in this table. We do So I'm blocking some filtering and things. I mean, these are relatively large problems. We have millions of record pairs that we're dealing with. Some of the results, I apologize for this giant table. I had a nice plot and then I lost it. So all I've done here is I've computed, again, I fit the model with conditional quasi-independence. I fit the model with conditional independence. The one of them accounts for the filtering and the structural zeros. The other one doesn't, okay, even though they're there. And we're going to sort of circle back to the point that Harvey made. The estimates of these matching weights, right? So on the left-hand side, the first 7 columns, those are just the comparison patterns. I'm showing you the weight over here under conditional quasi-independence that I estimate. The weight over here under conditional independence that I estimate. There is very little correspondence between the two once you get past the first 3 cells. You have rank order inversions, and you have truly crazy things. Like this weight under conditional independence is estimated to be negative, but those fields, they agreed on everything except postal code, right? But I've estimated that it is more likely than not that those record pairs are a non-match, okay? And that's because of the structural zeros and ignoring that when I fit this conditional independence model. Okay. So if we try to do something else, right? So I don't. I'm not going to talk about that. The estimates we get under conditional independence, treating structural zeros as sampling zeros, just don't make sense. They just don't make sense. And we get something that's a little bit better. We get decision rules that seem reasonable. In this case, I know the true match and non-match status based on clerical review. And we actually do a lot better. We get a rank order that makes more sense. We get parameter estimates that seem reasonable. They're not exactly right for a variety of reasons, but I think they're a lot better. Okay. So conclusions, how we block, how we index, how we filter, it has important implications for going on and inferring linkage structure, true match and non-match status. Okay. And the implications are more than just, well, if I block, I might actually, accidentally capture a few true matches and throw them away. Okay? The implications run much deeper than that. Falaky center has its drawbacks, as we've talked about, but widespread use after almost 50 years, there's a reason for that. Okay? I would sort of characterize this method as it's kind of like OLS, right? It works when you think maybe it shouldn't, and it can actually solve a lot of problems. But even relatively small improvements, and I'd argue that conditional quasi-independence is a fairly big one, can have a pretty big impact just because of how widely these things are used. So I better stop there. But again, like I said to Harvey initially, this is not the stopping point. I'm interested in sort of taking these insights and these models and pushing them forward to some of the more complicated things that we're doing. In particular, sort of these Bayesian methods that Becca and Mauricio and whole community of people are working on. Doing this filtering, doing indexing by disjunctions, reducing the space of possible matches is super important for those methods. Super important to scaling them up to real problems and getting things like uncertainty propagation and all these wonderful things that Becca talked about yesterday. So I'll stop there.
Thank you. A little bit of time for 1 or 2 questions. So we have afternoon coffee.
So I have 2 questions. The first one is, did you, in terms of the cancer registry, did you look at the impact of what the threshold has on the results? And then I just wondered if you have some further insights of taking a Bayesian spin on this.
So you've got true matches and non-matches on the right-hand side. So pick your threshold, right? I mean, you can slide it up and down. If you use the rank order estimated under conditional quasi-independence, which is how I've displayed it. Sorry, this is something I didn't tell you about here. So they're ordered by the weights that I estimated. If you just sort of eyeball it, the weights that you estimate using conditional independence are garbage. They give you a rank order that doesn't make a lot of sense, right? And in particular, the cell that I highlighted, right, I have 811 matches out of 813 observations. And conditional quasi-independence says, well, I'm not going to match that. Look at that weight, right? It's less than 0. You'd never take the threshold down that low. So you would miss those 800 matches, and I would pick them up. Yeah.
And in terms of beta?
So the kinds of models that I'm fitting here, they extend immediately to the comparison vector type things, right? The stuff that Mauricio does. I have some ideas for how you should think about doing that in the case where you're modeling raw data. So if you think about what blocking does, it changes the marginal distribution of unmatched records. We can be more precise afterwards, but it matters there too. It matters in terms of how you specify models, and it also does things like induce dependence between fields that maybe wouldn't have been there in the original file. It can actually change relationships and things. But we can.
One quick question. The second last row, just the number of non-matches is extremely low. If you look at the second last row, you have same first name, same day, month and year of birth, different family and different sex, and you have no non-match.
So this is actually a super easy problem. You have super high quality fields for all these things, which makes this performance more troubling. I'd also just say I truncated the table, right? So this table goes down another 100 and some odd rows, right? So the non-matches are down here. But yeah, I mean, this is a really easy problem, right? I mean, almost all of the matches agree on everything. And we really should be able to capture things like, oh, I just didn't agree on the postal code. But these sort of naive applications of conditional independence, validity center type methods would miss that. And I'll catch them. Yeah.
Does this procedure give you a message about when to stop blocking?
About when to stop blocking.
Stop blocking because you over-identify. You got too many. Your model's too big. You're overfitting them.
No, but it's interesting, right? Because if you think about what I'm doing when I do, let's just focus on filtering, right? So when I'm throwing away the record pairs near the 0 cell, there's a bias variance trade-off, right? My claim is that I can get better estimates of conditional error rates if I just focus on the portion of the table that's near the 1 cell. I haven't made that precise. It would be really interesting to do so and get some insight into how you'd actually do that. Yeah.
Thanks, Jared. So let's have a coffee break, and we will convene at 4 o'clock for the final session. Thank you.